Welcome to the GCSE Statistics Higher Session 8. This session is focused on the normal distribution and consists of three subsections: calculating the standard deviation, standardized scores, and control charts. Calculating the standard deviation. You need to be able to calculate this from individual values or from a grouped table. Almost inevitably, you are asked to calculate the mean, which will then be used for the standard deviation. The formulas you need are given inside the cover in various formats. We will have a look at those in a moment. Furthermore, you are usually given the sum of x squared or the sum of fx squared as appropriate to the question, which will save you time in calculating these for yourself. You'll sometimes ask what happens to the mean if you add an additional value. You just need to say it increases if the value is bigger than the mean, or decreases if the value is smaller than the mean. Two symbols you need to know as well, two Greek letters. Our first one here for the mean. The mean is known here as mu. And this is a mean of normal distributions. The standard deviation is denoted here by the letter sigma. This will help you, instead of writing out mean and standard deviation, using the notation will be quicker and more mathematically correct. So using those two notations will help us in this section. So let's take a look now at what's on the formula sheet. Here you can see the calculations needed to work out the mean and the standard deviation. We will have a look here at a few different examples. This one here is for a list, the mean of a list of data. Here we have a grouped frequency where x is the midpoint. So when you're multiplying your frequency, you're multiplying it by the midpoint. Again, the standard deviation, you need the mean to calculate the standard deviation. And we can see here that also this notation here for a set of numbers is also really important. Notice the notation here, x with a bar on top is equal to the mean of a set of numbers. So we're going to practice these different formulas and apply them to a number of different questions. Example number 1. The table shows information about the numbers of fatal road accidents in Great Britain. Here we have 2 years and we have the quarters, followed by the number of fatal road accidents in each one of these quarters. We're asked to calculate the mean number of fatal road accidents per quarter. So this is very simple. Here we take the sum of x divided by the sum of x here, adding up all of these, dividing by x, how many values that we have. So adding up each one of these to be able to find our total here of 6,422. We then divide this by 8, which will give us our mean of 802.75. We're then told that for the numbers of fatal road accidents in the table, the sum of x squared is equal to this value. So instead of squaring each one of these and adding them up, we have been provided here with the information we need to calculate the standard deviation. To calculate the standard deviation here, we will find this by taking the square root of the sum of x squared divided by n, how many numbers there are. Subtract the sum of x divided by n, this is the mean, this is what we calculated here. This is equal to the sum of x divided by n, the total number, all squared. So substituting in our values now, we have this value here. 5 million is going to go here. Our n value is 8. Here we have our value, 802.75, and then we're going to square it. Putting this into our calculator, the standard deviation, correct to one decimal place, is 71.7. We're then told that in the first quarter of 2006, that's the year after here, the number of fatal road accidents was 720. A motoring organisation is going to calculate the mean of fatal road accidents per quarter for 2004 to 2005 and the first quarter of 2006. Without carrying out any further calculations, compare this mean with the mean found in Part A. So let's have a look at the mean in Part A. In Part A, we have a mean of 802.75. This is from 2004 to 2005. We have here the first, this is per quarter, and we have here then the mean for the first quarter in 2006 as 720. This is calculated per quarter because we divided by 8. So we can compare these two values. And we can see that the first quarter of 2007, 720, is less than 802.75. Therefore, we can conclude that the mean has decreased. Example number 2. Here we're going to calculate the standard deviation from a table. We're first asked to work out an estimate for the mean parking time. Here, up in our table, we have group data. So we must calculate the midpoint. This is our value for x. So the midpoint between 0 and 1 is 0.5. 1 and 2, 1.5. 3, 5, and 9. Once we have our midpoints, we can then calculate fx, just like we're finding the mean from the grouped frequency table. So we're multiplying our frequency, this column, with our midpoint, this column for x. 16 times 0.5, 8, 36, 90, 120, 216. Now, to be able to calculate an estimate for mean, we need to find our sum, the total of fx, which is 470. We have here our total of f, that's the sum of the frequency already calculated for us. To be able to find an estimate for the mean, we take the sum of fx divided by the sum of f. So we have 470 all divided by 118, which gives us a mean of 3.98 hours. Now, work out an estimate for the standard deviation of these parking times. We're asked to give our answer correct to one decimal place. We must round correctly, and we've been provided with a value for the sum of fx squared. So using our formula, we can see from our page, if you look back at your sheet of formulas, the standard deviation here, where we have group frequency, is found by the square root of the sum of fx squared divided by the sum of f. Subtract, big brackets, the sum of fx divided by the sum of f all squared. Now this looks really complicated. Do not be put off. You can see here that this is the mean and that goes here. So we have our mean value, we square it. Here, this number fits in this part. Divide by the sum of the frequency, we know that already, which is equal to 118. So plugging all that into our calculator, if you work out the square root, what's underneath within the square root part first, we're calculating the square root of 8.4986. Correct one decimal place is 2.9. This is the standard deviation. Standardized scores. This is a standard question. To compare values from different data sets, you usually set up the standardized scores. The data must be normally distributed. And we need to use this here, where x is our value. We saw this Greek letter at the beginning, and this is equal to the mean. And this is the mean when the distribution is normally distributed. Sigma here is for standard deviation. So this is what we use to calculate standardized scores. A negative value just means below the population mean average. Standardization enables us to compare relative like with like. The standardized scores can indicate how many standard deviations a score is above or below the mean. So this is a really, really important part, which is often part of a question on standard deviation linked also with normal distribution. Example number 3 here. The table gives the mean and standard deviation of the marks in 3 examinations. The marks in each of these examinations are normally distributed. Here we've been given the mean and the standard deviation. Mean, standard deviation, sigma. Mary got a mark of 71 in the French exam. So Mary here got 72, reading here. And a mark of 66 in German. We're asked to calculate Mary's standardized scores for these examinations. So we must take the value, subtract the mean, and divide by the standard deviation. So let's look at French first. French, 72, the value she got for her French mark. Subtract the mean of French, 60. Divided by the standard deviation sigma, we have 15. Standardized score, 0.8. So this tells us how far above or below the mean. Here, 0.8 above, it's a positive number. Okay, to work out here now, her German mark, 66, take away the mean, in this case, 56, divided by the standard deviation of 10, gives us a standardized score of 1. And we're asked, did Mary do better in the French or the German exam? We need to look at our 2 standardized scores here. Whichever one is the larger one is the better mark. So we can see here that Mary has done better in German. Why? Higher, larger, standardized score. Here, standardized score. We are told that in the science examination, Mary had a standardized score of negative 0.56. And we're asked to calculate her science examination mark. So we're going to use the same formula here that we have and substitute in our values. So x, we don't know. This is Mary's mark. We're not sure. Subtract the mean. We have the mean here as 50. Divided by the standard deviation, 12.5, is equal to a standardized score of negative 0.56. So we're substituting in and then we're going to solve for x. So rearranging this, multiplying by 12.5, adding 50 will give a science mark of 43. So here you can see that Mary's mark is below the mean. The mean of the class is 50. Mary's mark is 43. That's why we have a negative standardized score. Whereas the other 2 standardized scores were positive. They were above the mean value for the class. Control charts. Quality control in the context of industrial manufacturing processes. You'll notice these questions and be able to spot them by the context that when it's to do with manufacturing, whether it's a production line, tins or something, or packages or weights of things being compared. Now, in real life, all products cannot be checked, as checking usually involves the product destruction. So if we're actually having to check the product, then the product will be destroyed. So only sample batches are taken to be tested. The sample mean is calculated for each batch, and if this mean is outside what is acceptable, the machine is stopped and then recalibrated. Now, the acceptable limits we can see here below are based on the normal distribution. The sample means can be plotted in a chart called the control chart. Now, this is related here to the normal distribution. First off, we have three different options. Our first one is a range of the mean plus or minus 1 standard deviation. And this gives us 68% of the distribution. If you look at this in terms of a normal distribution, we will have a bell-shaped curve. The line here in the middle is the mean, mu. We will then have a sketch, you can see here, of a bell-shaped curve and 1 standard deviation from the mean. So add 1, so plus 1 standard deviation here, and subtract 1 standard deviation. So here in the middle, we will have 68% of the distribution. Here it's saying that that leaves 16% outside the range in each tail. So here we have 16% above, and here we have 16% below. And this is the range of a mean plus or minus 1 standard deviation. If we change that to plus or minus 2 standard deviations, that will give us 95% of the distribution, leaving only 2.5% above and below. Furthermore, a range of a mean plus or minus 3 standard deviations, we have almost all of the population captured, 99.8%, leaving only 0.1% above and below in the range, outside of the range in each tail. Now, using this information, the manufacturer sets action limits of the second or third cases. So these here will be what the questions involve, a standard deviation, so a mean plus or minus standard deviation of 2 or 3. Again, as mentioned above, when a sample value strays outside of these limits, the machine will stop and be reset. Let's take a look at some of these questions now in context. Example number 4. A machine fills packets with roast peanuts. Bob takes a sample of 10 packets every hour. The mean weights of the samples are normally distributed, with a mean of 106 grams and a standard deviation of 2 grams. So if we do a little sketch to help us, the line in the middle is 106. Here we have our bell-shaped normal distribution. Standard deviation of 2 grams. We're asked to write down the percentage of samples that are likely to have a sample mean of less than 100 grams. So taking a look here, we have 106 here, so 100 is going to come before here. And we can see here that our difference between 106 and 100 is 6. How many standard deviations is that? Well, a standard deviation represents 2 grams. So a space here of 6 is 3 standard deviations. Looking back at the previous table, we can see that subtracting 3 standard deviations from the mean means that this section here represents 0.1% of the distribution. So here we can have, again, if we had the number on this side, plus 6, so that's 3 standard deviations, 112, the proportion of the population or the percentage of the population that is here, 3 standard deviations from the mean, add or subtract, is 99.8%. So less than this section here that I will now shade in the yellow, in the green here, this percent represents 0.1%. We're asked to write down the percentage of the samples that are likely to have a sample mean of more than 110. Taking out now, going back to the same diagram, you can see here 105, 110 will be here. 110 is plus 4, which is equal to 2 standard deviations. 2 standard deviations, here we can have on this side take away 4, 102. This section now is worth 95%. So more than 110, I will shade in here with the yellow. More than this part here represents 2.5%. We're told that Bob sets up a quality assurance chart for the means. Write down one reason why Bob would use a quality assurance chart. Now it's really important because Bob has a machine who's filling packets of peanuts and he needs to stop the process when it produces weights outside the allowable range. So this quality assurance chart enables the process of packaging to be stopped if the weight is outside of the allowable range. We're then told that the chart has a lower action limit of 100 grams. One sample mean is less than 100 grams. What should Bob do? So if the lower action limit is 100 grams and the sample mean comes out less than 100 grams, Bob needs to stop the machine and reset. So simply here, stop and reset, or stop and recalibrate. The next 2 sections, why should Bob also have an upper action limit? So if the weight gets too high, Bob also needs to stop the machine. Why does he need to stop the machine? Because if the packet gets too many peanuts in, this will affect his profit. So the reason for having an upper action limit is to limit the number of peanuts. Why? Because he wants to make sure that he has a profit. Lastly, you're asked, what sort of other quality assurance chart is Bob likely to use? So Bob might want to know about the variation, the spread, the distribution of the weights. To do that, he needs to use the range or the standard deviation. So the answer here to part C that's acceptable is the range or the standard deviation. Example number 5. We're told that on a production line in a factory, baked beans and tomato sauce are put in tins. The label on each tin says that the contents weigh 415 grams. Give 2 reasons why it's not practical to check the weight of the contents of each tin. Why? Practical reasons, too long, too time consuming. Also, it's going to be too expensive. Why? Because sampling involves the destruction of the product. So when we're sampling, we need to destroy the contents of the tin afterwards. So it's too expensive because sampling would destroy the tins. Secondly, we're told that the sample of tins are taken at intervals and the weights of the contents are found. This is known as batch sampling. It's been found that the mean weight of the samples is 417 grams. So the mu, the mean. The standard deviation is 0.6. we're told that the weights are normally distributed and asked between what limits would you expect 99.8% of the sample to lie? Well, we know that in a normal distribution for 99.8%, we need to have the range of the mean plus or minus 3 standard deviations. So let's have a look. We have the mean here at 417. Plus or minus, we'll do both, 3 times standard deviation 0.6. So the limits that we would expect, the lower bound, the lower limit of 415.2 and the upper limit of 418.8. We're told that the target weight is set at 417. Using our answer, here we have of part B, give a reason why the target weight of 417 rather than 415 is used. Well, we can see here that 415.2 is the lower bound and only 0.1% is below this level. Therefore, above this level is 99.9%. So by making the target weight 417, this means that 99.9% of the tins is greater than 415.2 grams. We can see that on a sketch of the distribution. We have a normal distribution. The target weight we have here set at 417. We have here the normal distribution, the bell-shaped curve. We have here 3 standard deviations of 415.2 and here our upper limit of 418.8. We can see here that everything above, by having our target weight of 417, the distribution above, all of the yellow part here, everything above 14.2 is equal to 99.9% of the distribution. The point just here is only 0.1%. This means that when this machine is working, 99.9% of the tins have a weight greater than 415.2 grams. We're then told that a sample of tins is taken each half an hour during a 6-hour shift, and the mean weight of the contents is found. We can see here the line across for the target weight, and then the mean weights here plotted. The allowable limits for the weights of the samples are plus or minus 3 standard deviations from the target weight. So on our previous page, we worked out that the target weight here, it goes up to 418.8, which is here. And then on the other side here, the lower limit, 415.2. So anything outside this range, action will be taken. So we can see here that we have one of the samples, the 11th sample, is above the allowable limits. So when asked to comment on any action that would have been taken during the 6-hour shift, you can state that at sample 11, the machine should be stopped and reset, because you can see here that the mean weight of the sample is above the allowable limit. So it's now time for you to complete some questions. Press pause on the video and complete the question booklet. Once you have done all the questions, come back to the video, press play, and we will be going through the questions together. Question number 1. In an experiment, a psychologist records the times X for 50 people to complete a puzzle. The results are summarized in the table. We can see here we have continuous data grouped for the times, and we have our frequency here for the number of people. Altogether, we have 50 people. We're asked first to work out an estimate for the mean time. We have to estimate the mean because we do not know here where the 10 people's times lie. So we calculate the midpoint for our X value. So halfway between 0 and 40 is 20. Our midpoint here, 50, 70, 90, and 140. We're finding the middle of each one of the class intervals. We then need to multiply our frequency by the midpoint X. So we are multiplying the values in these two columns. So Fx is 200, 450, 840, 810, 1400. Adding up all of these gives us the sum of Fx, which is 3,700. We then can find an estimate for the mean by taking the sum of Fx divided by the sum of the frequencies, which is equal to 3,700 divided by 50, which gives us an estimate for the mean at 74 minutes, or seconds in this case, sorry. We're then asked to show that the standard deviation for the times is approximately 40 seconds. So we've been given the answer, approximately 40 seconds. We now need to show it. So to be able to find the standard deviation, we must find the sum of Fx squared. So first, you will need to add a column for x squared, squaring each one of these numbers, and then finding Fx squared. Now, the two numbers we're interested in are the numbers after completing those two calculations for the total, here and here. These then substitute into the formula provided on the formula sheet for standard deviation of grouped data. We are looking at the sum of Fx squared. We must square the x first, multiplied by the frequency. That's this value here. We then divide by the sum of f, which we know is 50. And we subtract that from the mean squared. And we've already calculated that here in the first part. So we'll substitute in the 74 square. Put that into your calculator and we get the value of 40.1. So when it says show the standard deviation for the time is approximately 40 seconds, 40.1 is approximately 40 seconds. Question number 2. Working days were lost in the manufacturing industries and in the public administration and defence industries between August 2000 and May 2001 as a result of strikes. Here we have our two categories, manufacturing here and public defence and administration. Public administration and defence. The table shows the number of working days in thousands lost each year. So here we have our number of working days across the 2 years in the months. We're told that the mean number of working days lost in manufacturing is 5.7. So for manufacturing here, our mean is 5.7 thousand. We're then told that the standard deviation in public administration and defence is 5.3. And first off, we're asked to calculate the mean value of the number of working days lost each month in public administration and the defence industry. So we are looking here for the mean. We are going to find the mean by adding up all these values and dividing by the number of values. Adding up all of these numbers, we get 67. Divide by how many numbers? 10. And we have our mean value of 6.7. So here for the public administration and defence, our mean is 6.7, slightly higher than the mean in the manufacturing. The next part of the question asks us to find the standard deviation for the manufacturing here. Now we have a list of data. We can find the standard deviation by finding the square root of the sum of all of the values squared. So we need to take each one of these values, square it, add it up. So we're finding the sum of x squared. We're going to divide that by the number, we have 10, and we're going to subtract the mean squared. So that's the sum of x divided by n all squared, which is simply 5.7 squared. That's going in here. So substituting in our values into the different spaces, we have here our standard deviation is equal to the square root of 457. How? Square 14, square 4, square 2, add, square all the numbers, add them up, and you get 457. Divide by how many numbers? We have 10 numbers. So we are dividing by 10, and we're subtracting our mean. Don't work out the mean. We're told in the question that the mean here is 5.7. So 5.7 squared. Calculating that gives us a standard deviation of 3.6. So the standard deviation for the manufacturing industries is 3.6. Part B is explained in the original video, so you can go straight and edit with the original video for Part B of this question. Question number 3. 150 bags of sweets are weighed. The results are summarised in the table below. First off, we're asked to find an estimate for the mean weight of bags. Again, we have continuous data. We must find the midpoint first to multiply this by the frequency. Our midpoint for the first class interval, 95 to 99 here, the middle value 97. We then have 100, 102, 104, 106, 108, 110, and lastly here 113. You need to record the midpoints. This will be our x. Then we must multiply our frequency by our midpoint. So we're going to be multiplying our red numbers here with our frequency column. Check that you have the same answers that are appearing now in the FX column. By multiplying together the frequency with the midpoint, we're having to estimate here because we do not know exactly where each one of the frequency falls within the class interval. I've missed one here, so I have here this one. Okay, sorry, just one in here. Just missed it out as that's coming down. They're the next two, they need to shuffle along one. So our value here for 106 multiplied by 32 is 3,392, followed by 1,944. Just make sure that's a 1. 1,100. And lastly here, 1,356. Now, to estimate the mean, we're going to have the total, the sum of fx. So adding up all of the numbers in that column, we have 15,764 divided by the total frequency, which we have here in the question, and we also get by adding these up, should be 150, which gives us a mean weight, an estimate for the mean weight of 105.1 grams. In the next part, we're asked to calculate an estimate for the standard deviation of the weights of the 150 bags of sweets. To help us, the sum of FW squared is equal to the value here. So to be able to find the standard deviation, we just need to simply put this into our formula. So we take the sum of FW, or X, it doesn't matter, squared, and we divide by how many? We have 150. And then we subtract our sum of Fx squared, or Fw, if you kept in the same notation, divided by 150, the mean squared. Putting all that into your calculator will give a standard deviation of 3.8. Question number 4. The table here gives the mean and standard deviation of the times in seconds for each of 2 races in the Olympic Games of 2004. The times in each of these races are normally distributed. We're here told that Roman ran a time of 10.85 seconds in the 100-metre race and a time of 48.36 seconds in the 400-metre race. We're asked to calculate the standardized score. So remembering back to the standardized form, we take the value, we then subtract the mean and divide by the standard deviation. So first off, let's take a look at the 100-metre race. So Roman, his time was 10.85. We subtract the mean, we hear from the table, which is 10.95. So he's quicker than the mean. Dividing through by the standard deviation, 0.238, again from the table, along with 100 metres, we get a value here of minus 0.4201. Then looking towards the 400-metre race. Using exactly the same approach, his time, 48.36, subtract the mean, which for the 400 is 49.62, or divided by the standard deviation, 1.29, which is equal to negative 0.967. We're then asked to interpret the answers in part A. So we've got these 2 values, and they're the standardized score for this particular runners against the mean and the standard deviation in this Olympic Games. Which one did he do better in? Which one was he further away from the mean? The further away from the mean is the number that is more negative. This here was the better race. So we can interpret this by saying that 400 metres was the better race. He performed better in the 400. Why? Because the standardized form, the standardized score, is further from the mean. And we can see this here, it's more negative, further down from the mean. Question number 5. Tyson took a statistics test and a maths test. Both tests were marked out of 100. The table gives information about Tyson's mark. It also shows the mean mark and standard deviation of the group that took the test. First part, you need to work out the standardized scores for statistics and maths. Again, using the value, then subtract the mean, divided by the standard deviation, gives us a standardized score. So, in statistics, Tyson's mark was 55. Take away the group mean of 52. Divided by the standard deviation of 15. 3 over 15 into a decimal, 0.2. And then for maths, similarly, Tyson's mark, 48. subtract the mean, 45, divided by 12. And here we have 3 over 12, which is the same as 0.25. We're then asked to write down the subject in which Tyler did better and to give a reason. Which subject did he do better in? Tyson's score was better in maths. Why? Because his standardized score is higher. So which subject? Maths. Why? Because he has a higher standardized score. This means that his mark was further from the mean of the group. Therefore, he did better in maths than in statistics. We're then asked to comment on the group's performance in the two tests. So we just need to look at the group mean and the group standard deviation. So looking here, we can see that the group mean is higher for statistics. Both tests are out of 100. So in the group, the students did better in statistics. Or we could say that the statistics exam was easier because the mean mark was higher and the maths mark was harder. Looking at the standard deviation here, we can see that statistics has a higher standard deviation. This means that the statistic marks were more variable. So in the class, some people got higher marks and lower marks, whereas in the maths, the group variation was less. So when asking to make a comment here, 1 for the mean, 1 for the standard deviation. Question number 6. A machine fills packets with sugar. Each hour, Peter takes a sample of 10 packets. So we've got something to do with machinery, some industrial process, something about sampling. We know here that he's going to be sampling and taking 10 packets every hour. Asked about what type of sampling. This is systematic sampling. Why? Because it's periodic. He has planned that for every hour, he's taking a sample of 10 packets. So he has a set number for a period of time. In this case, 10 packets for an hour. We're then told that Peter calculates the mean weight for each sample of 10 packets, and that these mean weights are normally distributed, mean of 505 and a standard deviation of 1.6. We're asked to write down the percentage of samples that have a mean weight within 2 standard deviations of the mean. This is from what we learned from the very first page in relation to the control charts and what this means for the normal distribution, 95%. 2 standard deviations within 2 standard deviations. The mean is within 2 standard deviations of the mean, 95% of the distribution. We're then told the allowable limits for the mean weights are the mean plus or minus 3 standard deviations. Peter takes a sample. It has a mean weight of 500. What should he do? Okay, let's have a look at the limits here. So we have 505 plus or minus 3 times the standard deviation, which in this case we're told is 1.6. So we're looking here at a lower end, the 500 weight, so 505, subtract 3 times 1.6, gives us an answer of 502. This is the lower limit. So this equals the lower allowable limit. So anything lower than this will not be accepted. So Peter takes a sample. It has a mean weight of 500. 500 is less than 500.2. Therefore, Peter must stop and reset the machine. Question number 7. The weight of coffee in jars of ground coffee is normally distributed with a mean weight of 260 grams and a standard deviation of 4.5 grams. A jar of ground coffee is chosen at random. What is the probability that this jar of coffee weighs less than 251? Okay, so let's have a look here. If this is normally distributed, it says in the question, the line here is our mean, 260. Got a bell-shaped curve, remember it's just a sketch. And we're looking for 251. So it's going to be somewhere this side, 251. How far from the mean is this? Subtract 9. Standard deviation, 4.5. How many deviations? This is 2 times standard deviations. So if it's 2 times the standard deviation, we know that 2 times the standard deviation includes 95, the normally distributed. This part here is worth 95% of the distribution. So here we have 95%, sorry, no dot there, 95% of the distribution. This means we have 2.5% this side and 2.5% this side. Question is, what's the probability that a jar of coffee weighs less than 252? What's the probability? It's the percentage here, 2.5. Why? Because 251 is 2 standard deviations away from the mean. We're told here that jars of ground coffee have a weight marked of 250 E. The letter E shows that the weight of the coffee in the jar conforms to the mean weight standard. We're then told that the mean weight standard allows no more than 2.5% of the jars to contain less than the weight marked on the jar. So we're asked to discuss whether or not these jars of ground coffee conform to the mean weight. So we're looking here, 250 is here, further down in this side. So it's even less than 2.5%. So yes, these jars do conform. Why? Because it's less than, not even 2.5%, but less than 2.5% fall below 250 grams. So they conform. We see here that at 251 we have 2.5% of the distribution. So a further along 2.50 we must have less than 2.5%. Therefore, these jars conform to the mean weight standard. Question number 8. A steel manufacturer finds that the total quantity of raw materials used by his company each week is normally distributed with a mean of 1,000 tonnes and a standard deviation of 200 tonnes. We're asked to calculate an estimate of the maximum quantity of raw materials the company is likely to use per week. So, if we take a look at the normal distribution, the mean is 1,000. And here we have our distribution. So one standard deviation away is 1,200. 2 standard deviations away here is 1,400. And this contains here, between these two, 95% of the distribution. One standard deviation is going to be slightly too small. So here we have 95% at this point here, and then further along, 3 standard deviations is 1,600 tonnes, which contains 99.8% of the distribution. So the maximum quantity that is likely to be used is somewhere between 1,400 and 1,600. So somewhere between these two answers is correct. We're told that the manager of the steel manufacturing company decides to make a regular order for the same amount of raw materials to be delivered each week on a Monday. Discuss what would be a suitable figure for the quantity to be ordered. So a suitable figure. So we've got the mean, which is down the middle, the average, and we need to have a bit more than the mean. So one way to discuss, to plan the ordering would be to have the mean plus some more. And that should cover any extra things. We could have the mean plus one standard deviation. And that would be a bit more than a mean. So that would go up to 1,200. Now, the maximum that we worked out here to be between these two, this is likely to be wasteful if he's ordering it every single Monday, and it will build up too much stock. So if you were to suggest a suitable figure for a weekly delivery, you need to go for either of these options. Choosing your answer here to part A by ordering the maximum every single week would be wasteful and would result in stock building up. So a suitable figure would be somewhere between these two values here. We've now come to the end of session 8. Please review the list of subtopics shown here on the screen and replay the video for any sections that you would like to study again.